So today we have Kwangjun. He's a LIDS and ECS student. He's advised by Professor Straw. His research interests include optimization, probability and statistics, and random matrix theory. So before I turn it over to him, make sure everybody that you're muted. And if you have any questions, I think it might be best if you just do it over the chat box, and we'll let Kwangjun just look at that at his discretion. And so today, yeah, with that, go ahead, Kwangjun.
Okay, thank you for the introduction. Yeah. Since like today's topic, I'm gonna introduce you guys a new class of random matrices. It could be somewhat confusing, so just feel free to like interrupt me whenever you have any questions. By the way, can you guys hear me well?
Yeah, we can hear you.
Okay, yeah, just to make sure. Okay, so the title is Graph Matrices, and the main results will be norm bounds and their applications. This is a joint work with Dhruv Medarametla and Aaron Potechin. So Dhruv is a graduate student at Stanford, and Aaron Potechin is a professor at U Chicago. Okay, so let me get started. So for those who are not familiar with random matrix theory, let me briefly go through the brief background. So random matrix theory is a very important subject in mathematics with lots of applications, physics, computer science, and so on. But current understanding is mostly limited to the models where the entries are independent to each other. But the modern applications are requiring random matrices where the entries are not anymore independent. So let me start with a motivating example so that you can keep this in back of your head. So this example is from analyzing tensor decomposition algorithm by Rong-Ge and Teng-Yu Ma. So in their technical analysis, technical step, this supremum term arises where they need to bound this term in order to guarantee the performance of tensor decomposition algorithm. As you can see, this is really complicated term, but since it's a supremum over unit norm vector, you can see that with some modification, this is equal to this vector matrix vector product form, where the matrix in the center is n squared times n squared, the dimension matrix. But since there are some symmetry going on here, you can choose either this one over here on the top, or this one at the on the bottom. So there's two different choices you can make. And using this, you can actually upper bound this complicated supremum term by this spectral norm of random matrices. But then here two questions arise. First of all, these are already really complicated random matrix, so it's not clear how you can upper bound them. Even you manage to come up with some upper bound with some hard work. It's not sure which one to choose. So it might be the case that you do a really hard work and come up with an upper bound for the first one. It turns out the second one is the ground truth answer, the better answer, and you should have done some analysis for the second case. Okay, so since the class of random matrix called graph matrix I'm going to introduce is quite complicated, let me just give you some looking ahead trailer of what they are. So what I'm gonna do in this slide is I'm gonna represent this complicated random matrix that belongs to the first case as the graph matrix. So everything here is going to be informal, but bear with me. I'm gonna make this formal throughout the rest of the talk. But so since this is an n squared times n squared matrix, the entries will be to specify one entry. There will be we need 4 different indices among 1 to n. So, and then the entry corresponding to I1, I2, I3, I4 will look like this. But then if you unravel this inner product, you will see that the entry will be the summation of all these terms. And one naive way, maybe it's very informal statement what I'm going to make, but you can basically represent this by a picture like this. So for each I indices, you draw a circle, and for each j indices, you draw a diamond. So you can draw this 5 I indices and 2 diamonds like this. And then you can represent all this. These are, since AIs are AJs are random vectors. These are just random variables, you can very heuristically represent these random variables with edges based on the dependency on the indices. For example, here, a j1, I1 is represented by the edge between I1 and j1, and j1, I2, this random variable right here, can be represented by this edge right here. Similarly, term on the right can be represented by these two edges, and these first terms can be represented by these two edges. But we gotta specify which indices are specifying the row and column. So we just draw boxes around those 4 indices. These are for row, these are for column. So roughly speaking, graph matrices are just graphical representation of complicated random matrices. And I foreshadow here that this graphical representation will be called shape. Just so that I can give you one more example, let's consider the second type in the motivating example. Similarly, you can just draw just the dependency with this small shape, but then now the edge will be different because of just different choice like this. Yeah, so, and again, we're gonna call this small graph that captures the this dependency a shape. Okay, so given this motivating example, the goal of this talk will be about formalizing all of this. So we're gonna first introduce a new class of random matrices called graph matrices. And our main results will be norm bounds on such graph matrices. And it turns out applications are those norm bounds capture or recover the known results in the prior works, which actually requires some complicated analysis. Whereas here, if we use graph matrices, we can come up with the norm bounds really in a simple manner. Okay, so let me move on to the former definition of graph matrix. It's really helpful if you guys just keep those the motivating example throughout the definitions. So graph matrices, in a nutshell, it's a random matrix where the matrix depends on random graph input, but the dependence is captured by what I introduced earlier, shape, which is just a small graph. So let me first consider the simplified setting where there aren't any diamonds vertices. We're just going to consider the case where there's just single type of vertices. So for the random graph part, we're going to consider Erdős-Renyi. Those who are not familiar with this, it's just like there are n nodes, and for each pair ij, there's the plus minus 1 random variable associated to it, and they're independent random variables. So basically, for those who know Erdős-Renyi random graph, it's just basically plus minus 1 labeled Erdős-Renyi. And for the shape, the small graph that captures the dependency, we will consider the simplified setting where there's just one type, single type. But to make everything formal, we're gonna consider a shape is defined on shape is a graph on variables. So vertices here are variables. And we're gonna call vertices left, right, middle. So basically, what you wanna imagine are those these examples right here. So U alpha will be just like the motivating example. These will be just for the row indices, and V alpha, which we call right vertices, will be for the column indices. And there are going to be middle vertices like this. To increase the expressive power of this graph matrices. Okay, so based on these two ingredients, graph matrices are formally defined as this. So what I want you to focus on here is the n is the number of nodes in input random graph, and shape has L left nodes and R right vertices or right nodes. Then the graph matrix corresponding to the shape n alpha is this dimension random matrix, where then since dimension is like this, each entry is specified by L tuple as a row index and R tuple as a column index. And it's quite a complicated expression, but I'll break it down. So it's a summation over all injective map from this set of variables to this indices of this product term. This product term is nothing but, let me break it down. So you just apply map to these variables and you'll get this some kind of realized shape where all the variables in the vertices are replaced by actual indices like this. But because of this restriction, those corresponding to column and row and column, or left and right, or will be just i's and j's. But so it's not undetermined part will be just the middle vertices. Let's call them sigma w1. And what this is saying is basically just, since they're now indices, these edges corresponds to edge variable that we define for the input random graph. So we just take the product of all these edge variables from the input random graph, and there will be just this summand. So that's how I break it down. And one remark here is that if there's no middle vertex, then this sigma will be determined completely by the values of this row and column. So there will this summation will be just summation over a single term. Okay, so this is the definition. Since it looks complicated, let me go through some examples. That way you guys can understand it better. So first example is the simplest example. So consider this very simple shape where there are two vertices U1, V1, and just one edge. So let's see what graph matrix is corresponding to this shape. Then because of the definition, now it's just n times n matrix, where for I equal to j, when row index is equal to column index, there's no way these two different variables can be mapped injectively to a single index. So the entry corresponding to that will be just summation over nothing, which is 0. But for distinct ij, u will be mapped to I, v will be mapped to j. So what we're having is this realized shape. So the entry will be equal to the edge variable corresponding to ij. Okay. And putting it differently in a more familiar term, those who ever seen random matrix theory, this is nothing but just plus minus one regular model where M alpha is symmetric n times n matrix with 0 diagonals and off diagonal entries independently equal to just plus minus one uniformly. Okay, so one remark here is that even this single shape, very simple shape you can think of, gives recover this well-known model. So you can imagine that if you make things a little bit complicated, this will already give you really complicated random matrix. So let's see what this random matrix corresponding to this looks like. So it's an n times n minus 1 matrix. So again, if they're not distinct, there's no way to map this into these indices. So this will be just 0. But if they're distinct, the only undetermined part will be the value of the middle vertex, right? So just letting it k, then the realized shape will look like this. So the entry will be just the summation of the corresponding product of edge variables. So here it will be product of ik, kj1, kj2, just like this. And as you can see, this matrix is already very non-trivial, complicated random matrix. Okay, so I hope my examples and definitions were clear, and I'm going to move on to the first main theorem of this paper, which is about the norm bounds of this simplified case. So for that, it turns out the norm bound can be described or characterized by a combinatorial property of the shape that defines the random matrix. So the combinatorial property, it turns out to be related to vertex separator. So we call S is a vertex separator of alpha if there's no path between U alpha and V alpha after removing S. So basically, after removing S, you can imagine U alpha and V alpha are separated. With this quantity in mind, our main theorem states that the quantity of interest is actually turns out to be the minimum size vertex separator of alpha. So given the shape, the graph matrix corresponding to the shape has a norm bound looks like this, and there comes up the combinatorial property of the shape. And this basically this is saying is you just count the number of vertices not in the minimum size vertex separator and put it to the power of square root n. Okay. So for example, for this shape that we covered before, the norm bound will be square root n over, since the vertex separator will be either u1 or v1, it will be, the size will be just 1. So the norm bound will be square root n, which recovers the known results. Yeah, for those who are not familiar with the random matrix theory, this is very traditional results where Wegener model has the norm upper bounded by square root n. It's recovering the conventional result. But here, this wavy inequality means it's accurate up to polylogarithmic vectors. So there's some polylogarithmic terms. And so for the next example, since W1 is the minimum vertex separator, this norm bound of this will be n to the 1.5. Okay. So some remarks are in order. So it's very interesting because the shape combinatorial quantity of the shape characterizes the norm bound of the random graph matrix. And actually this upper bound is typed up to polylogarithmic vector because there's matching lower bound. It's also in our paper. And this results right here is interestingly already very useful for analyzing sum of square lower bounds. There are really powerful algorithms called sum of square algorithms. And there have been a lot of works trying to prove the lower bounds on them. That's just like background information. It turns out this is already very useful for technical part, like proof part of this famous paper on SOS lower bounds. Okay, but then, so far we consider simplified setting, but to be able to consider like a motivating example, we need to generalize this definition a little bit so that we can have this diamond vertices in the middle. So that's what I'm gonna do in this slide. So actually there is the general most definition in our paper, but then for the purpose of the talk, I'll just consider two types case. For the, yeah, again, the purpose of the talk. And so this random graph, now we, instead of having this plus minus one variable, we could have just, because like there are a lot of applications where they have Gaussian random variables. Now we allow them to be Gaussian, for example. And in order to capture those diamond vertices, we consider m additional nodes in the input random graph. And so on the shape side, there are all those things are taking values in 1 to n, and they can be described by just these circles. But we additionally consider special middle vertices, which can take values in 1 through m, and they're described by these diamonds. Okay, so for example, this will be the one. And these two examples that I covered in previous slide as a motivating example will be another examples too. Okay, so it turns out for this case, main theorem will read like as follows. So again, the main quantity of interest will be vertex separator. But then since there are two types of vertices, now we have to give them weights. So for this case, we're gonna give a circle weight 1 and diamond weight log n, a base n, m. Then the theorem tells the quantity of interest here will be S minimum, which is minimum weight vertex separator of the shape. Then again, the norm bounds can be characterized by this weight. But this just parse this expression. It's nothing but just for each circle, outside of the minimum vertex separator, you put this number into the power of square root n, and you do the same thing for the diamond vertex and put it into the exponent of square root n. Okay. So this exactly generalizes the simplified case, because there it was cardinality, but since the weight is 1, this is matching this. Okay, so this is just a generalization, but it turns out this bound will magically capture all these complicated examples in the literature. So before I go into the revisit the motivating example, let me first perhaps cover perhaps more well-known example to you guys. So in the analysis of principal component analysis, I actually came across this example recently while I was taking class. And it turns out we can capture this very classical result with random matrix too. So the original proof of this result requires some epsilon net argument and sub-Gaussian concentration. But we can just capture this with graph matrices. So this term is equal to this up to normalization. And turns out the off-diagonal part, we can capture with this simple random matrix, graph matrix. And the norm bound, just like we characterized from the previous slide. So it depends on the relative size between m and n. If m is smaller than n, then this is the minimum weight separator. So the norm bound will be square root n to the 2 power, which is just n, right? But if in the reverse, if m is larger than n, then this will be vertex separator, and the norm bound will be square root of n, right? So putting this together, the neat expression for this will be just maximum of this 2. And it turns out the off-diagonal part can be also similarly captured by graph matrix and gives the negligible term. So this is a norm bound. So putting back the normalization, you exactly recover this conventional result. So this is a warm-up. Okay, let me then revisit the motivating example. So this is a formal setting, and actually there's a relative size looks like this in their paper, and the goal was to upper bound these really complicated tilde. There's a question of what is tilde O. Tilde O is hiding a polylogarithmic vector. So the goal was to upper bound these two complicated random matrices. But what we saw earlier as a foreshadowing trailer was that there were both of these are graph matrices. But what's more, because of our norm bounds, we can quickly see which one is better. So revisiting the shapes that describes as graph matrices, we have these two terms. But so all we have to do, because of our main theorem, is to just figure out what's minimum vertex separator here. It turns out this is minimum vertex separator for here, first one. But for the second one, because of this well-connected structure, we need to delete 2 vertices at least. So since we're counting the exponent is was equal to the number of vertices not in the minimum vertex separator. So it turns out this will give the better bound. And actually, this is the case. That was the case in Ronga and Teng Ma's paper. But here, without going into complicated analysis like they did, we can just quickly see this is perhaps more insightful way of tackling the problem. And actually, it turns out the graph matrix norm bound, our main result, applied to this, gives a matching upper bound as Go and Ma's results. So since they're limited time, I'll just briefly mention what other application we were able to capture. So for this famous hypercontractivity paper, where they bound 2 to 4 norm of random operators, it's a really complex concept, but it turns out we can capture that with this simple graph matrix. And also this also interesting results by Hopkins et al. On analyzing fast spectral algorithms and sparse spectral recovery. We can actually capture that with this somewhat complicated but the norm bound will be easy because all we gotta do again is just compute the minimum weight separator. Okay, so let me conclude this talk with some remarks. So in this talk, I introduced a new class of random matrix called graph matrix to capture all these complicated random matrices arising in the analysis of algorithms and some sort in the literature. And we're able to actually capture many examples in the prior art, and even the very classical example of analysis of PCA turns out to be one application of graph matrix. So my personal recommendation is if you have a complicated random matrix at hand while you're tackling some research problem, try using graph matrices. So this is it. Hopefully I was able to introduce this concept to you guys in a limited time. And if there's any question, please send me an email, or you can just, ask me right now.
All right. So thanks, Kwangjun, for the talk. So I think we only have a